This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on limits at infinity. So our first example is the limit as x approaches positive infinity of 5x squared plus 3x plus 1 over x squared minus 4x plus 7. X is getting very large, 1,000, 100,000, 100 million. If that happens, what happens to this function? Where does this function go? Our algebraic process is to divide the top and bottom by the highest power in the bottom, which in this case is x squared. Divide the top by x squared, divide the bottom by x squared. If I divide the top by x squared, I divide each piece by x squared. Similarly, on the bottom, divide each piece by x squared. So 5x squared over x squared, 3x over x squared, 1 over x squared over x squared, 4x over x squared, 7 over x squared. 5x squared over x squared is 5. 3x over x squared becomes 3 over x. That's 1 over x squared. X squared over x squared is 1. This becomes 4 over x. That becomes 7 over x squared. Now, as these numbers get large, 3 over a million, 3 over a billion, basically 0. 1 over a million squared, 1 over a billion squared, basically 0. Similarly, as x gets large, 4 over x goes to 0, 7 over x squared goes to 0. A fixed number over an increasingly large number will always go to 0. So what we get here is 5 plus 0 over 1 minus 0 plus 0, and that result, of course, is just 5. So as x goes to infinity, this entire function goes to 5. Can we see that? So let's take a look at a graph. As x goes to positive infinity, what's happening to the function? And I've shown the graph out to about 35 or so, and you'll notice that it stabilizes. It seems to be getting closer and closer to 5. And you'll notice as it goes to negative infinity, it's also getting closer and closer to 5. But if we go back and look at the previous slide, if we had negative infinity instead, 3 over negative a million, 1 over negative a million quantity squared, 4 over negative a million, 7 over negative a million squared, the answer would be the same. It would still be 5 plus 0 over 1 minus 0 plus 0. So whether the function is going to positive infinity or negative infinity, the algebraic process is the same. So again, looking at this, as it goes to infinity, we can see it's going to 5. And we can make the argument that the limit as x goes to infinity of this function appears to be 5. We can also look at values. If I plug in various values for x, what is the function heading to? If I plug in 10, this function's at 7.925, not very close to 5. Plug in 100, 5.235, etc. Plug in 1,000, 5.02, etc. Plug in 10,000, 5.002. So it sure appears as we are approaching infinity, as the x numbers get increasingly large, the value of the function appears to be getting closer and closer to 5. So doing this problem 3 different ways, with algebraic analysis, with graphical analysis, and with a table. In each case, we can see that the limit as x approaches infinity of this function appears to be 5. Our next example is the limit as x goes to infinity of 2x squared plus 5x minus 1 over 7x cubed plus 4x squared plus 6x minus 3. What do we do first? We divide the top and the bottom by the highest power in the bottom, which is x cubed. Divide the top by x cubed, divide the bottom by x cubed. So each piece, 2x squared over x cubed plus 5x over x cubed minus 1 over x cubed, 7x cubed over x cubed plus 4x squared over x cubed plus 6x over x cubed minus 3 over x cubed. That's what this is going to look like. Now what happens here? X squared over x cubed is just going to give me 1 over x. That'll be 2 over x. This will be 5 over x squared. That will stay 1 over x cubed. This piece, the x cubes cancel. I just get 7. 4x squared over x cubed is 4 over x. 6x over x cubed is 6 over x squared. And that stays 3 over x cubed. So reducing all those fractions, we get this. As x goes to infinity, this goes to 0, 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 this goes to 7. Everything on top goes to 0, everything on the bottom goes to 7 plus 0 plus 0. So simplifying that, we just get 0 over 7, which of course is 0. If you have a bottom-heavy fraction, the degree of the bottom is higher than the degree of the top. As you approach infinity, the answer will be 0. And again, if you approach negative infinity instead, none of this changes. 2 over negative a million, 2 over negative a million squared, 1 over negative a million cubed. Those all go to 0. Similarly, those would all go to 0. So whether you go to positive infinity or negative infinity, we would expect from the algebra that the function is heading to 0, that that limit equals 0. And we can see that in the graph. I only need to go to 8 to see that this graph has an asymptote at 0. So as x gets large, the function is going to 0. So as x goes to positive infinity, the function is going to 0. Also, as x goes to negative infinity, you'll notice, as we said before, the function is going to 0. But we're focusing on positive infinity here, so we will say the limit as x goes to infinity of that function is 0. Let's look at a table as well. X's go to infinity. Let's plug in very, very large numbers and see what happens to this function. If I plug in 10, we get 0.0336. Plug in 100, 0029. Plug in 1,000, 0.0028626. So it certainly appears as if this could be going to 0 and reinforces our earlier work. Okay, our next example is the limit as x goes to infinity of 3x squared minus 7x plus 9 over 2x plus 6. I call this a top-heavy fraction because the degree of the top, x squared, is higher than any degree on the bottom. So how will that change things here? Our approach is the same. We divide the top and the bottom by the highest power in the bottom, which is x. Divide everything on top by x, divide everything on the bottom by x. 3x squared over x, 7x over x, 9 over x, 2x over x, 6x over x. 3x squared over x becomes 3x. 7x over x becomes 7. That becomes 9 over x. Downstairs we get 2 plus 6 over x. Don't forget to write the limits down on each step. Now, as x goes to infinity on the bottom, 6 over a million goes to 0, so the bottom just goes to 2. This goes to 0, this goes to negative and negative 7, but this keeps increasing. If x is a million, I get 3 million. So basically, the top is going to 3 million. Who cares about minus 7? Who cares about the 0? The top is basically 3 million. Who cares about 6 over a million? Basically 0, basically 2. 3 million over 2. You can see that that is increasing. X goes from a million to a billion. It keeps increasing. So the top is going to infinity. The bottom is going to 2. In this case, the limit does not exist. Now, can we see that? In this situation, as x gets large, and we're here at 40, you can see the way the function is heading. As x gets large, the function is just going to keep growing. In respect to negative infinity, as x goes to negative infinity, the function keeps heading that way. That would also go to, it's not going to stabilize, it's going to go to negative infinity. But our conclusion here is as x goes to infinity, this function goes to infinity. Some textbook authors say the limit equals infinity. I don't particularly like that because the limit doesn't exist. I hate to say the limit equals something if it doesn't exist. So I just feel better saying as x goes to infinity, that thing goes to infinity. And similarly, as x goes to negative infinity, the function keeps decreasing, and that function goes to negative infinity. And in either case, that never stabilizes, so the limit as x goes to infinity of the original question does not exist. Here's a table, plugging in 10, plugging in 100, 142, plugging in 1,000, 1492, plugging in 10,000, 14,992. These are just growing, 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 and growing. So this is more evidence that as x goes to infinity, this function just increases without bound. We'd say that limit does not exist. Some authors would say the limit equals positive infinity. I feel better saying it's tending. As x goes to infinity, that function 3x squared minus 7x plus 9 over 2x plus 6 is tending to infinity. Next example is limit as x goes to negative infinity of 5x squared plus 3x plus 1 over x squared minus 4x plus 7. So we've looked at this before, but we're going to go to negative infinity this time. Divide top and bottom by the highest power in the bottom. Divide by x squared, top and bottom, as we're going to negative infinity. 5 plus 3 over x plus 1 over x squared. 1 minus 4 over x plus 7 over x squared there. 3 over negative a million goes to 0. 1 over negative a million quantity squared goes to 0, etc. Goes to 0, goes to 0. It's just 5 over 1, which equals 5. So again, whether going to positive infinity or negative infinity, the algebraic approach is the same. How about the limit as x approaches 3 from the right of 7 over x minus 3? The first thing we always try with the limit is just to plug in the number. Now you can't plug in infinity. Infinity is not a number, but I can plug in 3. So if I try to plug that in, I get 7 over 3 minus 3, which is 7 over 0. If it were 0 over 0, I'd have a chance for the limit to exist, because 0 over 0 is undetermined. But if I have 7 over 0, that's undefined. So I know for sure the limit doesn't exist. But let's describe the behavior of the function as we approach 3 from the right. Looking at the picture, 3.1, 3.01, 3.001, the function seems to be going to positive infinity as we approach 3 from the right. So that's my point. As x approaches 3 from the right, 7 over x minus 3 is approaching positive infinity. And similarly, as I approach 3 from the left, 2.9, 2.99, it's heading this way. As we approach 3 from the left, 7 over x minus 3 is approaching negative infinity. You can also look at a table. 3.1 minus 1 is 0.1, 7 over 0.1 is 70. 3.01 minus 3.01, 7 over 0.01 is 700. 3.001 minus 3.001, 7 over 0.001 is 7,000. So as we are approaching 3 from the right, what's happening to these numbers? They're getting increasingly large, they're going to positive infinity. But I could also have approached it from the left. So 2.9, 2.99, 2.999, I get negative 70, negative 700, negative 7,000. So let me say, as x approaches 3 from the left, numbers to the left of 3, that function is heading towards negative infinity. But again, that limit doesn't exist. But we can describe the behavior by looking at numbers close to the value the limit is approaching. Our next example is the limit as x approaches 5 from the right of x minus 5 squared. Let's try to plug it in. What do you get? 5 minus 5 is 0, squared is 0, 2 over 0. 2 over 0, the limit doesn't exist. If it were 0 over 0, we'd have a chance, but 2 over 0, no way. The limit does not exist in that case. Looking at the picture, as I approach 5 from the right, the graph gets increasingly large. So as x approaches 5 from the right, this function goes to positive infinity. Similarly, as I approach 5 from the left, it also approaches positive infinity. Some authors would say, then the limit as x approaches 5 equals infinity, since it approaches the same thing from the left and the right. But I will conclude the following. I will say as x approaches 5, we will say 2 over x minus 5 squared approaches infinity. And that will conclude this lesson.